Section 6.5, Limits of Indeterminate Forms, L'Hopital's Rule. The objectives for today's lesson are 3. 1. Know the list of indeterminate forms. So in the previous lesson, we were working with two indeterminate forms, 0 over 0 and infinity over infinity. But they are other indeterminate forms, and we want to know the list of all of the indeterminate forms. However, the only two indeterminate forms for which you can use L'Hopital's rule are these. The second objective, know the indeterminate forms for which a special procedure must be used to find the limit, and the second and the third objectives are related. If you have such an indeterminate form, what do you need to do? Find a limit by first assuming that it exists, and then take the natural log of both sides. So what is the list of indeterminate forms? We're going to begin with objective 1. So here is our comprehensive list of indeterminate forms that you may get when you're working with limits. We've seen these two. These are the two for which you can use L'Hopital's rule. And then the other 5 fall into two classes. We have this class of two indeterminate forms. If you get either of these as you're working on a problem, you can't use L'Hopital's rule. So what you have to do is you have to rewrite your function by using algebra to try to make your indeterminate form be one of these two, so that you would be able to use L'Hopital's rule. And the third class of indeterminate forms are these 3. And these are the 3 for which you have to use that special procedure to find the limit. You have to begin by assuming that the limit exists and then taking the natural log of both sides. Now, what's an easy way of remembering these 3 as being one class of indeterminate forms for which you have to use that special procedure? Just remember, you took Mr. U's class when you were 18, and you'll have nightmares until you're 80. If we were in class, I would laugh with you. So that's our list of indeterminate forms. Now, before we go on to our example for the objective having to do with using that special procedure to find the limit when you have one of these 3 indeterminate forms, I'd like to show you some forms which are, they look kind of similar to some of these, but they're not indeterminate. They're determinate. So let's look at those. So the 4 that we're going to look at are actually determinate, meaning if you get one of these 4 forms, you'll know the answer to the problem. So if you get infinity plus infinity, the limit will be infinity. So it's determinate. It's not indeterminate. If you get negative infinity minus negative infinity, the limit will be negative infinity. If you have 0 to the infinity, the limit will be 0. And if you have 0 to the negative infinity, the limit will be infinity. Now these are, maybe you think like this one looks kind of like this one here, but the difference is this one here is indeterminate, because if you get this as you're working on a limit problem, it doesn't tell you what the limit is. That's why all of these forms up here are indeterminate, because they don't tell you what the limit is. But the 4 down here are determinate because they will tell you what the limit is. Okay, so let's look at an example here. We have the limit of sine of x to the x as x approaches 0 from the right side of 0. So the first thing that you should try is what we call direct substitution. You're going to see what you get when you substitute 0 for x in your function. So we would get sine of 0 to the 0. Right? What is sine of 0? Sine of 0 is 0. So you have 0 to the 0. Remember, you took Mr. U's class when you were 18, and you had you're going to have nightmares until you're 80. So it's one of those 3 indeterminate forms for which you need to use that special procedure. And what is that special procedure? You're going to assume that the limit exists. So let's get started with that. So now we know that we have to use that special procedure for this problem, because the indeterminate form that we get is one of those 3 for which we have to use that special procedure. So we begin by assuming that the limit exists. We assume that the limit exists and is equal to some value y. So that's our first step in using that special procedure. Assume the limit exists and is equal to y. The second step is to take the natural log of both sides of this equation. So you're going to take the natural log of the left side of the equation, and you're going to take the natural log of the right side of the equation. Okay, so what is the third step? The third step is you're going to rewrite the right side of the equation, and you're able to rewrite it in the way that I'm about to show you. You can write the limit first. So you write the limit as x approaches 0 from the right of the natural log of sine x to the x. And the reason why you're able to do this is because of the continuity of the natural log function and the definition of continuity. We won't go into details there, but that's the reason. So the next step is to go ahead and use properties of logarithms to rewrite the part that I just circled in green. So what can you do with properties of logarithms? Well, what you can do is you can bring this exponent to the front. And when you do that, you're going to get x times the natural log of sine x. Okay, so that's great. So what are we going to do now? Well, let's see what happens when we try direct substitution again. So we've done some work. We began with this indeterminate form, for which we know we have to use this special procedure. We began by assuming that the limit exists and is equal to y. We took the natural log of both sides of the equation. We rewrote the right side of the equation. We're using a property of logarithms to further rewrite the right side of the equation. Let's try direct substitution now on the right side to see what we get for this limit. So as x approaches 0 from the right, so you're going to have 0 times natural log of sine of 0. Sine of 0 is 0, so you have natural log of 0. Natural log of 0 is actually undefined, but x is approaching 0 from the right side of 0. And if you remember the graph of the natural log function, it looks like this. This is what the graph of the natural log function looks like. You have what we call a vertical asymptote at x is equal to 0. So what happens as x approaches 0 from the right side of 0? The values of the natural log function will approach negative infinity. This is what the graph of the natural log function looks like. So this value here will be negative infinity. So we're going to have 0 times negative infinity. Now look at that and compare it to one of the indeterminate forms from the previous slide. It looks like this one, but I don't have positive infinity, I have negative infinity, but in fact it makes no difference. It would be considered this indeterminate form. It's indeterminate, but we can't use L'Hopital's rule because it's not one of these. So what do we have to do? We have to use algebra to rewrite what we have so that it would be in an equivalent form, which would give us one of these two indeterminate forms. So let's see if we can accomplish that. All right, so let's continue where we left off, and we're going to go ahead and rewrite the right side of that equation. So I'm going to put a vertical bar here. Now we're going to continue. We have the natural log of y is equal to the limit as x approaches 0 from the right. So the question that we have is this: is there a way in which I can rewrite x times natural log of sine x in an algebraically equivalent way that would give me a different indeterminate form when I try direct substitution? There is, and here's how you're going to do it. You can, multiplying by x is what we have here, right? We have natural log of sine x being multiplied by x. But multiplying by x is the same as dividing by the reciprocal of x, which is 1 over x. So we can rewrite x times the natural log of sine x as the natural log of sine x divided by the reciprocal of x, 1 over x. And when you divide by 1 over x, it's the same as multiplying by x. And what is the purpose of doing this? The purpose of doing this is so that now we'll try direct substitution one more time for the limit on the right side, and we'd like to see if we can get a different indeterminate form. Specifically, can we get either 0 over 0 or infinity over infinity, which would allow us to use L'Hopital's rule. So we're going to do that. And so we're going to have, as x approaches 0 from the right, sine of x will approach 0, natural log of 0 will approach negative infinity, and as x approaches 0 from the right, 1 over x will approach positive infinity. So we get this indeterminate form. That's like what we have here. Infinity over infinity and negative infinity over infinity are considered equivalent for this purpose. It's like you can write negative 1 times infinity over infinity. So this is, in fact, an indeterminate form for which you can use L'Hopital's rule. So we're going to go ahead and continue by using L'Hopital's rule to evaluate the limit on the right side of this equation. So we have natural log of y is equal to the limit as x approaches 0 from the right. Again, we're able to use L'Hopital's rule because we get the indeterminate form, negative 1 times infinity over infinity. So we can use L'Hopital's rule. So now we need to take the derivative of the function in the numerator. So the derivative of natural log of sine x would be the derivative of natural log is 1 over the argument. Multiply that by the derivative of the inside function sine x using the chain rule. And the derivative of sine x is cosine x. So we have that. And over 1, okay? All of that over the derivative of 1 over x. How do you find the derivative of 1 over x? Well, you can write 1 over x. So let me do some scratch work here. The derivative with respect to x of 1 over x can be found by rewriting 1 over x as x to the negative 1 using properties of exponents. And then you can bring the exponent to the front and you'll have negative 1 times x to the negative 2. That's the power rule. So that derivative simplifies to 1 over negative 1 over x squared. So that's what we'll have here, negative 1 over x squared. And in fact, you can rewrite the numerator. You can see that the numerator is going to be cosine x over sine x, which you can write as cosine over sine is cotangent. So we're going to have cotangent x in the numerator. Okay, so now we have to continue from here. So again, whenever you do a problem like this, you're trying to rewrite what you have on the right side, and then after you do each rewritten step, you're going back and trying the limit to see if you get a value for the limit. So let's go ahead and do that right now. Let's see if we can evaluate the limit of the right side. But what we can do in some instances is to rewrite what we have here, and this is one of those cases where it might be easier for you to rewrite what you have before you try to find the limit. So let's go ahead and do that just doing some algebra here. So we have natural log of y is equal to the limit as x approaches 0 from the right. What we can do is dividing by negative 1 over x squared is the same as multiplying by the reciprocal of it, which is negative x squared, and then you have times cotangent x. But you may remember from pre-calculus or trigonometry that cotangent is the reciprocal of the tangent function. So using this, I can rewrite cotangent as 1 over tangent x, and when I do that, I will have this. So again, the purpose of me doing that is just to help me to evaluate the limit on the right side. So let's see if I'm able to do any better now that I have this. What is this limit? Try direct substitution. Well, it's easy enough. As you substitute 0 for x, the numerator will just go to 0. And for the denominator, what is the tangent of 0? Tangent is sine over cosine. Sine of 0 is 0. Cosine of 0 is 1. So tangent of 0 is 0 over 1, which is 0. So again, the purpose of doing the rewriting from here to here is just to help me with this limit. It's a little bit easier for us to think when our function is rewritten in this form. But the point is, we still get an indeterminate form. But good for us that it's one of those two for which we can use L'Hopital's rule. So we have to keep going. We use L'Hopital's rule again on the right side because we get the indeterminate form 0 over 0. So now we have natural log of y is equal to the limit as x approaches 0 from the right. And now we're going to take the derivative of the function in the numerator. The derivative of negative x squared is negative 2x. And we're going to take the derivative of the function in the denominator. And the derivative of tangent x is secant squared x. So again, after you do any rewriting step, you're going to try direct substitution again. So let's see if we're able to do that. So you're going to try direct substitution as x approaches 0 from the right. Negative 2x, negative 2 times 0 is 0. What about the denominator? What will that approach? Well, one thing that can help you is remembering some trigonometry. Remember that if you have secant of x, it is the reciprocal of the cosine function. So it's 1 over cosine of x. So if you have secant squared x, you actually have 1 over cosine of x squared. So what happens is you can rewrite secant squared x like this. And what happens as x approaches 0? What's cosine of 0? Cosine of 0 is 1. So you'll have 1 over 1 squared or just 1. So the denominator will approach 1. So this function, negative 2x over secant squared x, the limit of that function as x approaches 0 from the right is 0 over 1 or 0. So now we have natural log of y is equal to 0. So finally, what are we looking for? We're looking for this limit. This is what we're after. And at the very beginning of this problem, we found that the limit had this indeterminate form for which we have to use the special procedure. And we assumed at the very beginning that the limit exists and is equal to y. So that's what we're after. We're after y. Y will tell us the limit of the problem that we begin with. So we're almost there. Let's see how we can find y. So we went through all these steps and we got to here. But again, as I said, we're after y. So how do you find y? We have natural log of y is equal to 0. So you're going to go back to the algebraic definition of the logarithm. The base here is e. So using the algebraic definition of the logarithm, this means you have, if you write this logarithmic equation in exponential form, you have e to the 0 is y. And what is e to the 0? E to the 0 is 1. So y is equal to 1. And what is y? Y is the limit that we were after. So the limit that we were after is equal to 1. So the original problem was the limit of sine x to the x as x approaches 0 from the right. That's going to be equal to 1. Because we assumed that this limit was y, and we just found out that y is equal to 1. Again, to recap, we began with our original problem. Which was this. This was our original problem. And when we tried direct substitution, we got this indeterminate form. It's one of those 3 indeterminate forms for which you have to use that special procedure. Begin by assuming that the limit exists and is equal to y, and take the natural log of both sides of the equation. Go through all the steps until you find y, and that's the limit. That's the original problem that we were working on. So today we learned about the different indeterminate forms we can have. And we also looked at 3 indeterminate forms for which you have to use a special procedure to find the limit. And we saw an example where we use that special procedure by first assuming that the limit exists and is equal to y, and then taking the natural log of both sides, and we went through several steps for our example problem.